Tesla just activated the 55,000-ton Gigapress. After months of rumors and leaked supplier documents, the machine is live at Gigafactory, Texas, and it's already casting full Model 2 underbodies in 7 seconds flat. Not test parts, not prototypes, complete structural chassis ready for assembly. To put that in perspective, Toyota's best automation takes 45 seconds per body section using hundreds of welded parts. GM and Ford, even slower. So here's what nobody's talking about. If Tesla can build an entire car structure in the time it takes to read this sentence, how do traditional automakers survive the next 24 months? Traditional automotive presses from Idra and Buhler, the industry leaders, max out around 9,000 to 12,000 tons of clamping force. They produce medium-sized castings that still require dozens of welding steps, bolt connections, and subframe alignment. Each cycle takes 38 to 52 seconds, depending on part complexity. Tesla's 55,000-ton unit operates at nearly 5 times that force and completes full underbody castings in 7.2 seconds. That's not an incremental improvement. That's physics-defying acceleration. But here's the part that should worry every automotive executive. This isn't theoretical anymore. Suppliers close to the Texas facility confirmed the press ran 847 production cycles last Tuesday alone. That's over 12,000 cycles per day at current capacity. So when exactly did the rest of the industry plan to catch up? The secret isn't just brute force. Tesla developed a modified aluminum alloy with faster flow rates and higher thermal tolerance that lets molten metal fill a chassis mold over 4 meters long without microfractures or cold joints. Standard high-pressure die casting alloys can't move that fast without structural defects appearing during cooling. Traditional castings that size typically warp by 2 to 3 millimeters, creating alignment nightmares downstream. Tesla's parallel quench channel system keeps dimensional variance below 0.8 millimeters across the entire structure. Engineers at competing firms told suppliers that tolerance level shouldn't be possible on castings this large. Yet Tesla is hitting it on production runs, not lab samples. Then there's the engineering twist that leaked from supplier documentation 3 weeks ago. The 55,000-ton press doesn't use traditional single-injection casting. It operates with a dual-shot micro-infusion system that reinforces stress zones around hinge pillars and sill plates during the casting process itself. Think about what that means. Instead of casting a uniform structure and then adding reinforcement later, which adds steps, time, and cost, Tesla strengthens critical load-bearing areas while the metal is still molten. The result? Door hinges and structural connection points that can handle repeated stress for 300,000 miles without sagging or misalignment. Traditional multi-piece frames can't guarantee that consistency because every weld point introduces variance. Every bolt connection creates a potential failure point. Tesla eliminated hundreds of those variables with one machine. But here's where it gets interesting. Why engineer ultra-durable door hinges into a mass-market compact car? Why over-engineer structural support around entry points when most buyers won't notice for years? Tesla isn't targeting tech enthusiasts or performance buyers with the Model 2. Internal documents suggest the vehicle is engineered specifically for drivers over 60. Over the past 2 years, transportation safety data revealed a pattern that most automakers ignored. Seniors have significantly fewer high-speed collisions, but experience dramatically higher rates of parking lot impacts, low-speed side scrapes, and mobility-related entry-exit injuries. The most common complaint? Door operation. Doors that are too heavy, too stiff, or require awkward angles to open. Doors that sag over time, making them harder to close. Doors that don't stay open at the right angle when getting in or out. Tesla's single-piece Gigacast body with reinforced sill plates and hinge posts allows extra-wide doors without sacrificing structural rigidity. The dual-shot reinforcement means those doors can be opened and closed 50,000 times, roughly 15 years of daily use, without the alignment shifting even a fraction of a millimeter. When someone leans heavily on a door frame for support while entering the vehicle, traditional multi-piece structures gradually flex and develop stress cracks. Tesla's casting distributes that load across the entire integrated structure. After 150,000 miles, the door should close with the same force and alignment as day one. Now ask yourself, how many automakers are even thinking about door durability as a core engineering priority? How many are designing vehicles specifically around the physical needs of aging drivers? And if Tesla captures that demographic with a $25,000 EV that requires almost zero maintenance, what's left for everyone else? Let's talk about money, because this is where Tesla's advantage becomes genuinely unfair. A traditional compact car requires over 400 stamped panels welded into subframes, sealed, coated, then bolted into final body structure. Even the most efficient Japanese and Korean platforms average 18 to 22 labor hours per body in white. Every welding robot needs maintenance. Every alignment jig needs recalibration. Every quality control station pulls bodies off the line for rework when tolerances drift. Tesla's Gigacast process reduces that entire chain to one casting plus two reinforcement inserts. Total body and white labor time, 3.5 hours. But wait, there's more cost reduction hiding in the energy consumption data. A press this size should realistically draw 20 to 24 megawatts per cycle. Tesla's regenerative hydraulic system recaptures kinetic energy during the press release phase and feeds it back into the next cycle. Net consumption, around 11 megawatts. That's 40% less electricity per casting than conventional large format presses. Over a year of continuous operation, that difference saves millions in plant-level operating costs. Multiply that across 3 shifts running 6 days a week, and you're looking at energy savings that could fund an entire second production line. The leaked cost target? $198 per gigacast body. Compare that to the $780 to $1,500 range for equivalent multi-part steel assemblies among mainstream automakers. Tesla isn't competing on price. They're operating in a completely different cost structure. When your body in white costs 75% less than your competitors, you can add features they can't afford. Powered door actuators calibrated for gentle opening, anti-pinch sensors, structural padding at entry points, grab rails that lock directly into reinforced casting zones. All the ergonomic features seniors actually want. Here's the part nobody's saying out loud yet. If Tesla can produce a structurally superior vehicle body in 7 seconds at $198 per unit, while competitors need 45 plus seconds and $780 plus per unit, the cost gap isn't closable with incremental improvements. You can't optimize your way out of a 5-to-1 disadvantage in cycle time. You can't engineering tweak your way to 75% cost reduction. The only option is to build an entirely new factory around entirely new equipment using entirely new processes. That takes 3 to 4 years minimum, billions in capital investment, complete supply chain restructuring, and even then, you're copying Tesla's 2025 technology while they're already iterating on the next generation. Industry analysts estimated that catching up to Tesla's current casting capability would require $8 to $12 billion in combined investment from legacy automakers. But here's the problem. Tesla didn't wait for them to catch up. They started mass production. Some suppliers are quietly projecting that, by mid-2026, Tesla could be producing Model 2 bodies faster than Ford produces entire F-150 trucks. Not comparable vehicles, entire trucks from frame to finish. Let that sink in for a moment. The best-selling vehicle in America for 47 consecutive years could be getting outproduced by a compact EV aimed at retirees. How does the industry respond to that? The 55,000-ton press at Gigafactory Texas is already operational. Not testing, not commissioning, operational. That means tooling is finalized. Supply chains are locked. Production workflows are validated. Tesla could theoretically start customer deliveries within 90 days if regulatory approvals clear. Meanwhile, GM's Ultium platform, their answer to Tesla's gigacasting, won't see comparable integration until late 2026 at the earliest. Ford's plans for structural casting don't show up in product roadmaps until 2027. Volkswagen's Project Trinity, which was supposed to be their technological leap forward, got delayed indefinitely last month. The gap isn't narrowing, it's expanding. And the 55,000-ton press isn't even Tesla's final form. Supplier documentation mentions a 70,000-ton prototype already under construction for Gigafactory Berlin. If that machine goes live in 2026, Tesla could theoretically cast entire vehicle structures, front, rear, and underbody, in a single 12-second sequence. At that point, traditional automotive manufacturing doesn't just become obsolete, it becomes economically impossible. So when we ask how traditional automakers survive the next 24 months, we're not being dramatic. We're asking a legitimate question about industrial viability. Because right now, while legacy manufacturers are still debating casting strategies in board meetings, Tesla is producing finished vehicle bodies faster than most companies can stamp a single door panel. So here's the answer to that opening question. Yes, we're witnessing the inflection point, but it's not just about one machine or one vehicle. Tesla's 55,000-ton press proves that automotive manufacturing can operate at computational speed instead of mechanical speed. 7 seconds to build what takes competitors 45 minutes. That's not competition, that's category disruption. And this is just Texas. The 70,000-ton prototype in Berlin could be operational by Q3 2026, capable of full-body single-shot casting in under 12 seconds. If that timeline holds, legacy automakers won't have years to adapt. They'll have months. The question isn't whether they can catch up anymore. It's whether they'll still be manufacturing cars by the time they try. What happens next? Watch the supplier networks. When Tier 1 manufacturers start canceling stamping contracts and pivoting to casting partnerships, that's your signal that the industry sees what's coming. This is Tesla Zone, where we break down the technology reshaping transportation before it hits mainstream headlines. What do you think moves faster? Tesla's production timeline or the industry's response? Drop your prediction below. The revolution isn't coming. It's already running production cycles.